In this video, we're going to determine the electronic geometry, the molecular geometry, and the hybridization of chlorine in the following polyatomic anions, namely hypochlorite, chlorite, chlorate, and perchlorate. So all of these polyatomic anions involve chlorine and oxygen. We will start off by locating oxygen and chlorine in the periodic table. So here, oxygen and chlorine. Oxygen, take note, that belongs to the group 6 of the periodic table. So in terms of valence, which are the electrons that participates in bonding, oxygen has 6 valence electrons and chlorine has 7 valence electrons. Also take note of the electronegativities of both 3.5 for oxygen, 3.0 for chlorine. Now, electronegativities are important in deciding for the structure, especially most of the time the one that has a lower electronegativity is chosen as a central atom. The horizontal periods are also important. So for oxygen, it belongs to N equals 2, energy level 2. Chlorine belongs to N is equal to 3. So this tells us that for oxygen, its electrons, its outer electrons belong to the 2s2, 2p6 orbitals. And for chlorine, 3s2, 3p6 orbital. This tells us that oxygen strictly follows the octet rule. Unlike for chlorine, if it needs more electrons to cater, then it can open the 3d orbitals. Now we will determine if the 3d orbital is needed for these 4 examples that we're going to discuss here. But take note that for level 2, they strictly follow the octet rule. That is, they will have 8 electrons in their outer energy level, which is energy level 2. Now that would help us to determine the structure. Now let's do it. So let's draw the structure for both chlorine and oxygen. We know that the valence electrons are, for chlorine it's 7 and for oxygen it's 6. And don't forget that it is a polyatomic anion with a negative charge of 1. So that means there's an extra 1 electron. So where do we place it? Do we place it in chlorine or do we place it with oxygen? We place it with oxygen because it's more electronegative. That means it attracts electrons more to itself. Now, since oxygen strictly follows the octet rule and it has 7 now, after we place the electron here, let's just give this 1 electron from chlorine to oxygen. So that here, each of the 4 orbitals in energy level 2 for oxygen are filled. So we can say that this is S2, then we have this 3p orbitals now. So we have 8 electrons in the outer energy level for oxygen. So here, chlorine and oxygen forms a linear bond, but in terms of electronic geometry for chlorine, the electronic geometry is tetrahedral. Tetrahedral because in molecular geometry, we count the number of lone pairs other than the bonds. So tetrahedral, we have 3 lone pairs plus 1 single bond. So we count that. So by the way, we have 4 electron groups here. So number of electron groups are 4. Electron groups or steric number is 4. So in an electron group, we count lone pairs plus single bond plus double bond plus triple bond as 1. Okay. Now the molecular geometry is linear. So the structure of hypochlorite is tetrahedral due to this electron groups. So that tells us that these electron groups and the single bond here are arranged in a tetrahedral separation in order to minimize that repulsion. So if they're arranged in the tetrahedral manner, then that is favorable because they repel, each electron groups are repelled by each other. Now it's linear because in molecular geometry, we only consider the bonded atoms with our, for example, here we're talking about chlorine. So the number of atoms bonded with chlorine is 1. So it is linear. So we only consider this bond here in deciding for the molecular geometry. Now, lastly, let's talk about the hybridization for chlorine. Right? We're not going to name it as a central atom here for now, but in others, it's going to be the central atom. For this one, chlorine, the electronic configuration is same as that of neon plus 3s2 and 3p5. So up, down, single, because of repulsion then before pairing up. Now it's going to say thank you to oxygen because of this one electron. So that now it is S2p6. And take note that in forming this hybridized orbitals, how many s orbitals participated? 1. How many p orbitals participated? 3. So we call this hybridization as sp3. Alright, so I think we discussed everything here from electronic geometry, molecular geometry, and hybridization. Take note that we determined the structure easily because we considered that oxygen strictly follows the octet rule. So that's why we gave 1 electron to oxygen. Also, we added 1 here because this is an ion with an extra 1 electron. And we gave it to oxygen with a higher electronegativity, 3.5, as compared to chlorine, which is 3.0. Again, 3.5, 3.0. Now we can do this fast now, knowing that chlorine should be the central atom, right? How? The one with a lower electronegativity is often chosen as a central atom because it tends to give more of its electron compared to the other element. So we have ClO2. It's important to read the name first. So ClO2 minus. So there's an extra -1 electron. So where do we give it? So we'll give it to this oxygen. So there you go, you have an electron. So -1. It only needs 1. Now we'll give this 1 electron here to oxygen so that oxygen now has 2 for each of the 4 orbitals in the S2p6, the outer energy level, the energy level 2. So here, this oxygen has 6. So it will need 2 electrons from chlorine to be shared with it. So we pair these two to fill 1 orbital, up, down. And we share this one to fill up another of oxygen's orbital. So the structure for chlorite is one that has a single bond and a double bond. So we can redraw that. So we just redraw the structure to make it more presentable. So again, it has 4 electron groups, just like the first one. So electron groups is equal to 4. How do we count electron groups or steric number? We count steric number electron groups by the number of lone pairs plus single bond plus double bond. So this is the electron group with respect to chlorine. So again, this is made up of 2 lone pairs, 1, 2, 1 single bond, and 1 double bond. So 1, 2, 3, 4. That is the number of electron groups. So these electron groups, which contains electrons, are separated with each other in a tetrahedral arrangement. So by the way, this double bond here, you have to notice that it is composed of a sigma bond and composed of a pi bond. If ever you encounter a triple bond, then a triple bond is composed of 1 sigma bond and 2 pi bonds. So it's always the case that you have a sigma bond which is head-on within the axis between the 2 nucleus of the 2 interacting atoms. Then you have a pi bond that is sideways. So you should take a look at picture for pi bond. Alright, so the electronic geometry is still the same. That is tetrahedral. And the molecular geometry, although the electronic geometry is tetrahedral, this one is now different. It is actually bent or angular. Why bent? If we can also draw this in a different manner, like we can place the lone pair this side, and then we have the double bond here, and then we have a single bond here. Okay, so for the hybridization of chlorine in chlorite is, so we're drawing the orbital rotation. Up, down, single, single, single. This is the electronic geometry for chlorine on its own. In forming a sigma bond, by the way, this is also sigma bond here. So in forming a sigma bond, we need 2 half-filled orbitals. So we relocate this 1 electron to a different set of orbitals so that we can erase it and then place it in one of the orbitals available for chlorine, which is the 3D orbitals. We want 2 half-filled orbitals to form a sigma bond with 2 of this oxygen, and then we place 1 electron here so that our hybridized orbital would look like this, where oxygen will place 2 of its electrons here, So we will place 2 of its electrons here, and then we have an extra d orbitals. So we have an extra electron in the d orbitals, wherein this electron is actually the one that forms the pi bond with this oxygen. So sigma sigma, this one half filled, this is the electron from oxygen, this one electron from this oxygen, and then this extra electron here forms the pi bond with this oxygen. So still the hybridization is, it's not sp3d, it is sp3 still. Hybridization is still sp3. Hybridization is the count of number of orbitals that has a lone pair plus the ones that cater sigma bonds. So here, this one contains a lone pair, contains a lone pair, that makes it 2. And then we have 2 orbitals here that caters for a sigma bond, sigma and then sigma. So how many, what are the orbitals that did that? It's the s and then 3p. So it's sp3 hybridization. So we don't count the orbital here that contains an electron that forms a pi bond. Alright, so only lone pair and sigma bond orbitals that we count for the hybridization. Let's do this fast for chlorate. Chlorine has 7 electrons again, and then we will surround this with oxygen. So we will bestow this oxygen with an extra electron, -1, so we place it with this oxygen, and then we have 2 more oxygens. So we will bestow this oxygen with another electron from chlorine. So oxygen here needs 2 more electrons to have 8 electrons, to have S2P6, and this one also 2 electrons from our central atom chlorine. Now the structure is again tetrahedral. Why? Because the steric number or electron groups is 4. 1 lone pair, 1 sigma bond, plus 2 double bonds. So the steric number or the number of electron group is 1 from that lone pair, 1 from a single bond, and 2 from the double bonds, for a total of 4 electron groups, steric number of 4. Now there's no need to redraw the structure. We know that this has an electronic geometry of tetrahedral and a molecular geometry of trigonal pyramidal. So for the hybridization of chlorine, let's draw the electron configuration of chlorine. So to determine the hybridization, we should count how many lone pairs and sigma bonds are present in this polyatomic anion. So here we have 1 lone pair, so we'll leave it to this one, and then we have 1 sigma bond here, 1 sigma, and we have 2 pi bonds here. So that means we have to leave 3 orbitals half filled because of these 3 sigma bonds. So, okay, so these 2 orbitals with a pair will lose 1 of its electron, and it will be placed in the 3d orbital, and then this one also 3d orbital. So we're talking about chlorine, which is in level 3, which is capable of expanding its orbitals, so that these 3 half-filled orbitals are meant to cater sigma bonds from these 3 oxygens. So this half-filled for sigma bond with this oxygen, this half-filled for a sigma bond with this oxygen, and then this half-filled for a sigma bond with this oxygen. And we have 2 electrons here for the pi bonds with these 2 oxygen, right? So for hybridization, the hybridized orbitals, we count only the number of orbitals that cater for lone pair and sigma bonds. So that's 1, 2, 3, 4. And then those orbitals are sp3. So it's still sp3. Up to the last, which is perchlorate, it's still sp3. So in this series of chlorine polyatomic anions from, let's see here, hypochlorite to chlorite to chlorate to perchlorate, they are all tetrahedral and they vary in terms of molecular geometry. The hybridization for all is sp3. Okay, so let's do the last one, which is perchlorate. And we will bestow that extra electron to this oxygen. Alright, so we have oxygens with 7, 6, 6, 6 electrons and chlorine with 7, of course. Now we will give 1 electron to this oxygen. This one needs 2 from chlorine. And yep, so that we have a structure with an electronic geometry of tetrahedral and molecular geometry of tetrahedral. Now, how about the hybridization for chlorine, our central atom? Alright, so this is the electron configuration for a single chlorine. Now, it's not single anymore. It will have a hybridized orbital. So, let's count the number of lone pairs and sigma bond in this new structure. A single bond contains 1 sigma bond. A double bond contains 1 sigma and 1 pi. This one contains 1 sigma and 1 pi. Sigma, 1 pi. So if we have a sigma bond, you need half-filled orbitals. How many we need? 4. And we don't have a lone pair here. So chlorine doesn't have a lone pair. So we're going to draw a new hybridized orbital that has lone pairs each. So take note, we have 7 for this one. We should know where each electrons are going. And then we're going to open up the 3D orbitals for chlorine. So this is S, P, and the D's. And then we remove 3. Move here, move here, move here. So that these 3 electrons that we moved are the ones that participate in pi bonding. And then we have here 4 orbitals for sigma bonds. So that allows this oxygen to have electron here. This oxygen for that sigma bond and sigma bond. And then 3 pi bonds. 1, 2, and 3. So the hybridized orbital is named as sp3. Again, the hybridized orbital is the count of number of orbitals that creates a lone pair and sigma bond. We ignore the pi bond, which are sideways overlap. So it's always here sp3. How about the previous one? It's sp3, sp3, okay. Alright, so there you go. So I hope you learned something in this video about molecular geometry, VSEPR, and valence bond theory. With that, thank you for watching.